Okay, thanks everyone for coming to this talk, which is something of direct interest to all of us in the business of archiving data, astronomy or otherwise. And so we're going to hear from Rich Wolski and Karan Celik of University of California, Santa Barbara. The title is Some Experimental Thinking About Community Data Lakes. And I'll hand it over to you, Rich.
Thank you. Thank you so much. Thanks everybody for coming. Let me do that screen share again. Hopefully you can see that. Right, so Kerem is a very, very talented student who did the work that you're about to hear about as part of his thesis. And just not talking out of school, he's probably going to be looking for a job here really soon. I want to start out by saying, this is not a talk that's intended to try and sell you anything. We were really doing an exploratory study. The work was funded by VMware. They were really interested in infrastructure and not the traditional NSF kind of research results. And so we thought we would try to flesh out some ideas from a very computer sciencey perspective. So ordinarily, I feel a little embarrassed about putting on my computer science hat in front of people who actually do real science for a living. But you'll have to bear with me while I do that during this talk. It's not intended to say this is the way we should do something on SCiMMA. It's intended to flesh out some of the ideas in a very, very concrete and experimental way. Okay, so let's start by motivating where this came from. For the past few years, we've been really working on computing for climate resilience, mostly in agriculture and ecology. There are a lot of folks who have been concerned, particularly in California, about climate change for a while. The effects are very, very noticeable out here, particularly with respect to the drought. And we've been working with them to try and build infrastructure in very remote places. Wildfire management, land use management, and animal migration, lots and lots of agriculture. And what we've come to believe is that in order for technology to penetrate the community, to become this ubiquitous thing, you really have to engage the community. And this is kind of at odds with how we do, computer science research, at least. I was just at a talk, I was just giving a talk at a meeting where we were discussing how we were going to deal with carbon footprint and try to get try to do computing around carbon footprint. And we were really the only talk that talked about the community. Everybody was saying, this is what we're telling you about carbon footprint, but in order to gain adoption, you really need to engage the community in this space. And I'll explain what that community looks like here in a minute. So the original goal for this work was to really look at what it would take to create a community-facing data lake so that we could all collaborate, the community could collaborate on trying to define and then use carbon footprint metrics and analytics. Okay, so what's a data lake? This is not something that gets written up in computer science textbooks these days, although it will be at some point, I suspect. As near as I can tell, it's originally due to James Dixon of Pentaho. And the original usage was to contrast with what he was calling a data mart, which is a place where curated data that has a schema and has gone through some ETL mechanism and some cataloging is available. Today, I think the contrast is a little different. We typically talk about data lakes as platforms where data is stored in raw format, and sometimes they're called schemaless, and where ETL takes place on demand. So you might have lots of raw data and then different ETL transformations in a catalog and choose, I want to do this one or I want to do that one. In contrast with the data warehouse, where there's kind of a barrier to entry, where in order to ingress the data, you must transform it to meet some kind of schema. And that's so that you know what's in the data warehouse is worth looking at, right? Its provenance and so on and so forth are essentially sort of handled up front. And you know, in some sense, a data warehouse is synonymous with a database where we have very, very large historical data collections. In other contexts, use the term data warehouse to mean a column store. And again, it's because you're doing this very, very historical kinds of things. But the key difference from our perspective is this notion that you can do ETL lazily in a data lake, and you don't necessarily in a data warehouse. Okay, so when do you use each? They're both useful. It's our perception that a data lake is useful when you don't really know what queries you're going to wind up wanting to do when you gather the data. So this is very true in this carbon metric space. Nobody really knows what we need to do to be able to generate these metrics. But we think that a lot of this data is useful, and we just haven't figured out how to combine it yet. We haven't figured out what the analytics are yet. Also, we think it's useful when some of the data sets that you want to work with, you anticipate. They're not there yet. There's large historical data, but someone comes up with a new thing, or citizen scientists, or crowdsourcing, or something, and you need to be able to combine this unseen data, which may have a very, very different sort of structure or unstructured from your data warehouse, and you don't want to just block because that data is not available. So we think that's sort of the use cases, or those are the use case characteristics. The costs are this ETL is applied sort of literally just before you use the data, and that can be an extensive operation. There's a latency associated with ETL for some ETL, not all, but there's definitely some latency, and that can be long. Also, doing this transformation is a coding task. What really motivated us to look at this from a practical perspective is we were talking with another research group that was scraping carbon footprint data from the web. There are publicly available data sets. They're very, very hard to work with. And they were spending hours, if not days, writing these scraping scripts and then maintaining them, which are essentially an ETL function. And so so there's a coding task there that you need to take seriously in order to be able to deal with this unstructured data in any meaningful way. Okay. So our thesis here then is in a community contribution setting where we're trying to encourage different entities, agencies, people, researchers to contribute data, it lowers the barrier to contribution. And in particular, we wanted to look at what happens when we disassociate data contributors from data users. So you can put something into a data lake in whatever form. It's somebody else's job in some sense to figure out how to do the ETL. The consumer of this data, in fact, is much more motivated to use the data than perhaps you are if you're a contributor. So we kind of decided that we're gonna push those two things apart if we could. But we're also gonna make it community facing. And to be community facing, it has to be a transparent system. Contributors and users must be able to discover, what's happening to the data, who's using it, and reason about that. Otherwise, there are entities who won't contribute. There are folks who will be very suspicious of it. We've had a lot of experience with this. It has to be auditable. And I'll define that. I'm using this term colloquially here, but I'll define it concretely later. And so you need to be able to understand after the fact what has happened to this data. Where did it come from? How has it become part of some aggregation? Many cycles down the road. It has to be access control, clearly. And this is a thorny issue. We don't have anything approaching a final finding about this. I'll explain what we're doing today, which is a little bit like GitHub, but it's interesting. This is something that can be done. It can be done at a very, very fine grain, but it looks weird from a computer science perspective. And it's got to be really, really easy to use and scalable and cheap. If it's community facing, it has to be community sustainable. I've built systems for NSF for a long time now. And the thing that now I think about before I start building anything is how do I sustain it? because they're just not in the business of keeping these things alive, even when there's community uptake. And so I was at a Google meeting and I was talking to my friends there, and we were talking about search and what have you, and they said, if you're giving something away for free, it better be really cheap to produce. And so we took that kind of as a mantra for this system as well. So the usual use case is this carbon metrics thing. And we wanted to really build a system that allowed, the exploration of these, by many, many different kinds of members of the community, hopefully in real time. The system that I'm presenting today, or we're presenting today, is not a real-time system, but we have plans for how it might be able to become one. The data sources, the potential contributors here are independent service operators. These are organizations that operate various kinds of transmission and distribution mechanisms, commonly called the electrical grid, and they operate at a regional level. They have publicly available data because of regulatory requirements, but it's very, very difficult to use, and it's often obfuscated, almost looks intentionally obfuscated. And these are very trust-challenged people or organizations. Power utilities that use the ISOs as their distribution mechanisms, they actually have ground truth on fuel mix and consumption, but there are privacy obligations, national security obligations, so on and so forth, that really prevent them from publishing this data, even if they wish to, and it's not clear that they do, but they have data to contribute. There are government agencies who have very, very strong publication incentives, but it's not clear that the data that they're publishing is tremendously accurate. Citizen scientists who wander around looking at solar farms and making inferences about what those solar farms or wind farms are doing. And these people are often motivated by civic planning interests, which are considerable at the local level, particularly in rural spaces. And researchers. It's not clear how you take all that data and make something useful out of it, but we believe that you can. So DIBB, Dependency Eager Platform of Transformations, which is Kerem's work, is a software platform for doing this. And it has a very, very specific model, which I'll try to codify here. First off, all data is immutable in version. It's an append-only system. Once you contribute data, it's there. It's there in the version that it is, and it will not change. One can, and this is needed for this transparency and auditing and provenance, right? You can't put data up there and then have it change. And this comes from our experience in agriculture. Nothing engenders suspicion more than having a data set disappear, or worse, suddenly the data is different. And the people who are looking at it don't know why. So this immutable version thing is really rooted in our interest in maintaining or building a trust architecture for the system. Code that transforms the data is attached to each version. So we have this exploratory notion where you have this raw data, or you have data that's in tabular form, and you wish to transform it in some way, which I'll sort of display graphically for you. Is part of this. You build these ETL programs for your specific need, but then once you've ETL'd it, you take that program and you couple it with the data, and that becomes a thing which the system manages. The transformation is lazy, so you can define this definition and you can build this ETL program, but not actually apply the ETL at that moment. And this is useful as a deduplication strategy. It's also useful in that there are lots and lots of versions of data. Data may be updated, and you may not need to materialize a data set or the dependencies, the things that depend on that data set every time new data arrives. That's something that this system allows you to separate out so that it can be much more space efficient. All data sets have an owner that sets an access policy and a retention policy. And for reasons that were not obvious, at least to me when we started, those policies need to be public. Okay, DIBBs has also a bunch of specific abstractions. A data set is a versioned data object and some metadata describing its outlet, and then potentially an ETL program associated if it's a managed data set. A transformation is a program. It is an actual piece of code that takes data sets as inputs and produces data sets as outputs. DIBB maintains a dependency graph. So your data set is either raw, just was ingressed, or it's a result of performing transformations on one or more upstream data sets. And that graph of transformations the system maintains. And there's two kinds of dependencies that this graph can take, two dependency forms of graph can take, strong and weak. Strong dependencies essentially make a guarantee about the ability to materialize the thing at the end of the graph. So you have this set of dependencies that go to build a data set. And if you choose to make it a strong dependency, then that materialization will be charged against your quota. The system is quoted. Weak dependencies are not charged, but there's not a guarantee that you can actually build the thing because an upstream may have timed out or been deleted, or the access control policies, may have changed, something of that nature. So you sort of get weak dependencies for free, which is useful for exploratory reasons, but they're not quoted, and you have to be able to switch between the two. This incidentally explains why policies need to be public, because you need to make a decision about what's going to happen upstream from you in order to materialize your data, which means you have to see the policy. And there's questions about privacy guarantees that we can discuss. Materialization is a process of applying a transformation to a data set.
Kerem?
Yeah.
You have a question in chat from James.
Sorry,
Rollins.
I can't see the chat, so by all means.
So I figured I'd just pipe up and let ask it. Jameson, if you'd like to unmute and ask it yourself, feel free.
By all means.
So Jameson asks, what is meant by versioned data in the context of immutable data?
Yeah, so you define a data set, which is essentially a provenance notion. This is where the data comes from. This is when it arrived. And then if you update that data, there's a new version of it. So the data that's there is there. An update to that data produces a new version of that data set. And so you can see the history of updates. No updates are ever lost. This is not for time series data. So let me be very, very clear. This is not a real-time system. This is not a system that's every time you add a new value to a very, very large data set, it's going to create a new data version for you. You could do it that way. And if there were very, very aggressive deduplication, that actually might be reasonably space efficient, but there isn't in the current implementation. So this is more along the lines of, I don't know, CalISO drops its map of distribution centers, once a month. Okay, every month you get a new version of that data set, but you don't lose the previous month's data. Okay, does that answer the question?
Yep.
Great, thank you. Sorry, I can't see the chat. By all means, interrupt. Just speak up. Or I will just keep talking endlessly. Okay, so there's a notion of materialization, which is to say there's a dependency and now you want to make something out of it. What we make out of it today is a Spark table. So you take this raw data, you apply ETL to essentially generate something that then is queryable and manageable in Spark, which is a big data in memory thing, for doing queries mainly, and also analytics. An announcement is the idea that this dependency exists and could be materialized. So you can see what's possible, but you don't necessarily have to burn the Spark time, the ETL time, the volume time, space in your cloud or whatever to materialize something that's been announced. So announcements are small. This graph is small. The data can be very, very large, and you have to pay the ETL cost to do the materialization in terms of the execution time and CPU and so on and so forth. And then there's this notion of something that's a policy. And right now we have access control and data retention. The access control looks like GitHub. But you can make this as rich as you'd like. I just don't know how you manage it in this graph entirely. But I have some ideas. Okay, so this is what this graph looks like. Over on the left-hand side, you've got these kind of raw data sets. But when you apply a transformation, which is code, ahead of that, there's some policy that dictates whether this code can be executed. And then you wind up with essentially a Spark table or a Spark data set. And this whole thing then is a data set, which then can be used, as an input to another transformation. So you have these arbitrary graphs, and Kerem has a lovely demo of what this looks like. Okay, so that's the model. That's this kind of computer sciencey way we're thinking about this. And there's really two challenges, only one of which we've investigated so far. So there's this discovery challenge, which is how do you figure out what's there, and how do you know what you want to use, what its persistence characteristics are? What's the reasoning model about this collection of data? Given that the community, right, people from all walks of life, if you will, are interacting with it. And this is really what we've been thinking about so far. And then there's the stewardship question, which is, how do you build a trust architecture and a timeline for that trust architecture so that folks know, okay, this is the real deal. I can trust the metadata here. I know this is going to be here in 5 years, this kind of thing. And we at SCiMMA are thinking about this as well, of course. And we don't have an experimental answer to that question, but there are a lot of research challenges that I think that it brings up. So this is what the current prototype looks like. It's all open source. This is for real. It runs at UCSB. We are in alpha testing, and we will probably go into beta testing on next Monday. The access control policies that are there are GitHub repo lookalikes. There's a retention policy, which is basically a time duration associated with each version of a data set. There's nothing more sophisticated than that. The front end is a Jupyter Lab notebook interface, which Kerem is going to demo for you here in a moment. And then this all runs at UCSB in our large campus cloud that Adam and I built way back when as part of the Aristotle project, but which now UCSB uses as its infrastructure. And what happens there, this is an AWS lookalike. So if you haven't seen Eucalyptus, it's an AWS open source knockoff that works at about data center scale as opposed to planetary scale. And but so what we do is we launch a bunch of instances in this cloud, and then Spark in those instances. And Spark is storing things in the instances and then launching other VMs for the ETL transformations, and then the raw data is stored in that S3 lookalike. The key thing about this, though, is that this thing supports quotas. And we have a way to implement a quota system. I don't know how you do this as pay as you go, frankly, just because the model is such a shared model. It's hard to know who to charge. But okay, so I will stop sharing there and invite Kerem, who you can see there, to give you a demo of what this thing looks like for real. Go for it, Kerem.
Okay. Hi, everyone. I'll be walking you through Depot from the perspective of researchers studying power generation and energy efficiency in California. So we'll go through a chronology of events that these researchers invoke, which in practice would span multiple users and organizations over arbitrary timespans. We'll do this without an explicit goal that we work towards to really emulate in practice how research end state is not always known beforehand, and just how Depot decouples data ingestion, transformation, and analysis. So in this demo, we'll observe the actions of 3 Depot users, Alice, Bob, and Charlie, who are studying California's carbon footprint with respect to power plants. And anyone who's worked with California energy data knows data is publicly available from many different sources, like the various balancing authorities, or the Federal Energy Information Agency, the EIA, or the California Energy Commission, the CEC. But data is in typically a variety of formats, reported at different intervals, and even comes sometimes in domain models that are not always compatible. For example, the EIA provides per power plant data, per power plant generations and emissions data, but the CEC reports power plant metadata, such as the fuel types they're equipped to consume, or the geographic locational data. And importantly, these two organizations identify individual power plants with completely different IDs. That being said, Alice has found a way to reconcile these IDs, or a way to map power plant info between data reported by the CEC to its EIA counterpart. Our next researcher, Bob, is exploring EIA emissions data and generation reports, and he's found a public-facing EIA site with historical data available. And our third researcher, Charlie, is interested in regional power generation and emissions. So I'll walk you through the steps that these researchers take. Alice has no immediate use for her file, so she's going to contribute it to Depot in the hopes, like Rich mentioned, that one day she or another researcher will find it useful. So through the Depot interface, she'll upload her file, she'll provide an alias for the file name, and she'll fill out some dataset overview info, defining the dataset, naming it, configuring access to it, and create the dataset. So here she introduces us to the dataset interface, or the central source of authority for dataset metadata, where consumers go to get an overview of a dataset and can even inspect down here sample data. She'll then show us the listing of the segments, which are the numbered versions of a dataset. And as we can see, the segment that we have here is in the materialized state, which is one of the two states that segments can primarily rest in. Either announced, meaning the transformations have not yet consumed any input data to persist the output data, or materialized, meaning transformations have run against input data, produced an output, and stored that output somewhere. In this case, Alice has just uploaded a file, so there's no transformation or inputs relevant here. So the file that she uploaded simply becomes the next instantly materialized segment of this data set. And as we saw from the sample data, though, it's really insufficient. The data is hard to look at, it's hard to parse, and it's hard to consume. So Alice decides that she'd like to wrangle this data into a more consumable and distributable format. So she'll spin up the integrated notebook interface to see how she can work with the data. And if you've used Jupyter Lab, this probably should invoke similar feelings. It's built on top of that, which is an open source project that enables rapid prototyping of code. It's typically bundled alongside or used alongside with Python and even Spark for data analysis purposes. That's the same stack we've chosen because it's basically ubiquitous, it's powerful, and it's flexible. So in this interface, she'll write some code that references the data set she just created. She can use some bash integrations to sanity check the data quickly. And next, she can use the Python Spark bindings to parse that JSON data into a Spark table or a data frame. She can then inspect the schema of that table. And satisfied with the results, she can publish it back to Depot. Like we've seen for the file data set, she fills out the overview, the information, the access controls, which in this case she'll leave as set. But unlike the first data set she created, there's some more knobs to turn here. One of those is the evaluation strategy, which controls how new segments of that data set are announced. And in this case, she's referenced her first data set, so she can configure this one as a dependency and have this one kept up to date as that parent data set is updated. She can also configure a materialization strategy, which controls when and how, or precisely when, a new segment of this data set will have its transformation run against inputs and persist it. In this case, this is just exploratory data. She doesn't want to be billed for either or she doesn't want to consume any compute or storage, so she'll leave it as manual. She'll say that her segments can live forever. And she'll keep the weak availability class and create that data set. When she creates this data set, the exploratory notebook that we just saw is published alongside that data set and becomes the transformation associated with it. And because she's published it as a table, shortly we'll see that the data set interface will give us a little more information than we've seen before. For this data set, for example, there's a fixed schema associated with it. And there's also more detailed sample data, although in this case, there's no materialized segments yet to show as sample. We can also see the lineage of this data set, or the dependency tree. And we see that it depends on the first data set she created from that file. And in the segments listing, we'll see that she now has one announced data set or segment that's not materialized yet. That depends on the data set version for the file that she uploaded. Now, Alice has contributed 2 data sets to DIBB. We can focus on Bob instead. As mentioned, Bob is another researcher, and he's found historical power plant data from the EIA sites, and he'll also use the notebook interface to scrape this data. He'll be using the Python request library, which allows him to perform HTTP requests to scrape the data in Python. He'll bring in the imports, and he'll configure the endpoints necessary to scrape. And he'll use the request library to scrape the last 12 years worth of data. And like Alice, he'll use the Python Spark interface to transform his scrape data into a table. We'll also take a look at the schema of that table. And he too will publish it to DIBBs, spilling out the information like we've seen before. In this case, his evaluation strategy can only be isolated because he's not referenced any parent data sets explicitly. He's got no dependencies, or he's not dependent on any other parent data sets, which means that new segments of this data set will be announced subject to the materialization schedule, which he sets to 48 hours. He chooses a segment, 7-day segment lifetime, and because he's got no dependence, or because his data set is not dependent on any others, the availability class option is irrelevant and disabled. Here we see a similar interface with a fixed schema. And from the lineage graph, you'll see this data set has no upstream. We can see the segment listing like we had before. And next, we can actually even see the code associated with this data set that is run every 48 hours to produce a new version. And as mentioned, Bob is also interested in generation data, so he'll use a similar EIA site to scrape power plant generation data. He'll fill out the parameters like we've seen before, and like we've seen before as well, he'll scrape 12 years worth of data. Then it goes into a Spark table. And going through the motions of publishing the DIBBs again. We'll choose the same arguments for the various policies and strategies. And we see his new data set here. Bob can then go and request explicitly manual materialization of a segment of his data set. So in this case, he's just requested that his generation data set be materialized, which again means to produce it, whatever that may mean. In this case, since there are no dependencies associated with it, what it means to materialize is to run that the exploratory notebook published with that data set, which has just completed. So now we see his segments in the materialized state, and we can take a closer look at the timeline of events that conspired or transpired for this segment. Let's look at that in slow motion. So we see the various states that the segment has gone through. And now that it's materialized, we get a sense of how big or how much space that data set occupies, or this version of that data set occupies. Now we can look at Charlie. Charlie, again, is another researcher. He's interested in regional power plant efficiency data. And by perusing Depot, he's found that Alice and Bob have created very useful data sets to him. So he'd like to see if he can work with those data sets to produce something of value to him. So we'll use the notebook interface. He'll reference Alice and Bob's data sets and bring them into his execution environment. And first, he'll filter data power plants that have generated more than 0 megawatt hours of electricity with pipeline natural gas as their primary fuel source. He'll then join that data set or that table with the emissions table, and then join that table with Alice's mapping table that allows him to associate a latitude longitude with his power plant. And that's the schema of the table that he ends up with. And he too can publish it back to Depot. And in this case, there's a triggered evaluation strategy available because he's referenced other data sets. He's shown here updates to which data sets, when triggered, would cause a new segment of his data set to be announced. And feeling impatient, he sets a 15-minute materialization strategy. He'll keep segments of this data set around for at least 48 hours. And he'll create a data set. And crucially, in this process, Charlie didn't have to do any of the data searching or the scraping or the transformation work because the heavy lifting had already been done for him by Alice and Bob with their data sets. And his data set is automatically dynamic. Changes to Alice's data set will result in new segments being announced in his data set, which he or another consumer can then request materialization from. So we can see in the data set interface here that his data set is a little more complicated in that it does more parents. We see how Alice's dependency tree is basically a root tier, or a path, we should say. And for an individual segment, we can inspect which versions of segment parents this segment is dependent on. Charlie can also, again, request explicit materialization of his data set, and we'll look at what that looks like at the parent. So if you recall, this is Alice's table data set. It was not materialized, it was an announced state. Charlie requesting materialization of his data set forced her data set to materialize, with Charlie bearing the cost. And we'll see the same for Bob's emissions data set. But for the generation data set, we'll see that because it's already materialized, Charlie requesting materialization on his data set caused no changes here. This really highlights just how cheap data exploration can be if you're conservative about what you force upstream to be materialized and stored. Now, Charlie can consume that data set he just created for analysis using the same Jupyter Notebook interface. Like we've seen a few times before, first he'll reference that data set he's interested in working with. And he's going to be using a Python mapping library. Mapping is in cartography, and called IPyLeaflet. So he'll load all the power plants he put in that parent data set, and he'll compute an efficiency score, an efficiency factor, which is just the pounds of CO2 emitted per megawatt hour of natural gas, megawatt hour electricity generated from natural gas, pipeline natural gas. And then it'll put that into a format that the mapping library accepts. They'll assign each power plant a color code based on a gradient of efficiency. And it'll plot the data for 2020 on a map, which is an interactive map, which will show us here. He'll show us now how we can programmatically interact with the map, and he'll animate the last 12 years worth of efficiency factors or emissions for those power plants. And we can see the animation play out on the map he just created. And if Charlie wants also, he can take that segment he was just playing around with in the notebook and download it for offline processing. We also see here there's a discrepancy between the shallow size of this segment and the retained size. The shallow size refers to how much space his segment, the table, is taking up on disk. And the retained size is how much space the parents are taking up on disk. And now we can go full circle and take a look at Alice again. Also, I see there are the chat bubble. Okay, well, looks like that's from a while ago, so we can handle those or take a look at those later. So we've gone full circle, we're back to Alice. Since we've last seen Alice, a new power plant has been constructed in California and her data set is now stale. As you recall, she uploaded from a file on her computer. She's just updated that file and now she's going to put it back into Depot. So we'll see what that looks like. A similar process to what we've seen in the beginning. She uploads a file and she attaches the alias, in this case plants.json. And now she's got 2 segments of our data set. A new version 2. And we can look at Charlie's data sets to see what's going on there. Now Charlie has a brand new announced segment. And if we inspect its dependencies, we'll see that it's dependent on version 2 of Alice's file data set. And the same can be said for Alice's table data set, which she wrangled from the file. Okay, that's it for Alice, Bob, and Charlie. That's where the story ends, but maybe we'll see some of you on Depot in the near future soon. Thanks.
Thanks, Kerem. Okay, and so I will just finish up and maybe give you all a little bit of, let's see, okay, there we go. A little bit of sort of thought questions that have come out of what you've seen. So the first question that really jumped out was, how do you do the accounting here? It's easy if every time you create a dependency, you get charged for that dependency, but that's not very space efficient and not very sustainable. It's great if you're Amazon. That's Amazon's business model. We want all your data. But here, if it's really a community sort of collaborative thing, you want to only store the data that you need. And that creates this kind of sharing relationship where not entirely clear who should be charged for upstream dependencies and this kind of thing. And so there's definitely some research to be done about that. I think it's interesting. And there's this weird thing where you add access controls or retention policies. If I've got a downstream dependency and the upstream times out, what does that mean for me? Right now, we've got this choice. You can either say, no, you have to force the retention and charge me for that forcing function, or I'm willing to take the idea that I can't materialize this data set at some point in the future because I'm not really sure I'm going to want it. And I think as these things get deeper, you want more and more. You're not really going to express these materializations unless you're interested in what's going on. But at the other end of this, you might. So I think there's an interesting question that jumps out there. If we're really going to try to do this shared accounting thing and not go to this thing where you just pay for anything you might use. So this is the strong and weak idea. But so quotas, we can build a quota system. It looks like a regular quota system, which is here's your limit. You don't really know, halting problem, if you're going to run over the limit when you produce a data set on a Linux system. If you run a simulation, you might think you know how big it is, but if the size of what your output is data dependent, you might blow your quota or not. And this has that same properties. We can build a quota system that feels like a quota system. I don't know how you do the charging. If you're actually going to charge dollars for this in an AWS or other public cloud, that sounds hard, but interesting. So that was what motivated us to do this in a quota supporting cloud. Then there's this business about policy. Right now, what Kerem has demoed for you, the policies are public, private, and you can create policies that govern or that are governed by that take as inputs by what is in the data tables themselves. It's not too long before you want to start making policies that are based on metadata. So, okay, Karan, I see your question. So, you'd like to say something like, okay, I want to do this transformation if Rich hasn't updated this field, or if this version is not due to Rich, because we don't trust him. Okay, good. So that's actually how you want to build real access controls. But then there's some questions about that. Are these mutable? GitHub didn't have a way to make something private once it was public originally, and I think I understand why that is. So what happens if you've got a downstream dependency and someone's upstream policy changes? Do you revoke access? This kind of thing. And then what are the access controls on the policy objects? If I define a policy, who can see it? And that's because you're deciding on sort of what your retention policy is for the thing that's a dependency. So you need to see something. Right now, there is as public as the data sets they govern, and they can't become less public. But there's a real privacy guarantee question, which is, if you can see that this dependency doesn't trust me, we're leaking that information. This is pachyderm. I don't know about pachyderm. But I will learn about it.
I can answer this one.
Great, thank you.
But so, yeah, there are lots or various kind of DAG, directed acyclic graph oriented data pipeline technologies like Dagster, pachyderm, or companies providing managed airflow or data flow. Depot's key difference in that it's community facing first, which you really can't take one of these other services and adapt to be community facing because it's not clear just how these storage, it's not clear who pays for what. It's not clear if you go upstream or downstream how your compute gets translated upstream. For example, in the demo, we saw Charlie materializing some data sets that forced materialization of a parent data set. It's absolutely not acceptable for Alice to be charged to run that transformation when it's Charlie's when Charlie is the reason it's running in the first place. It's also not acceptable for Alice to be billed for storing that data set because Alice just defined the transformation. She's not interested in, she said that her materialization should only be done manually. So she shouldn't be billed for storage or compute based on Charlie's actions. Does that make sense?
Yeah, I think so my comment would be the reason why I mentioned pachyderm and not Dagster is I think pachyderm also has a similar fundamental notion of data versioning and immutable data sets and, building on top of a Git methodology. So I do understand obviously Dagster and systems like Airflow, they are very different from what at least the demo showed. My just comment was, that it does have similarity to pachyderm, but it's true, pachyderm is a commercial for-profit enterprise.
Yeah, I think from the perspective of an individual byte of data, on these systems, you're probably going to go through the same series of steps. At some point, you're stored, and then when activated, you're run against a set of inputs and materialized. But Depot's focus is making this possible in a community environment to all sorts of various and non-mutually trusting producers and consumers.
Thank you.
Yeah, the trust model is a little bit different here, but yeah, I mean, and I want to be clear, we're not inventing this from scratch. So this is kind of what happens when you put these ideas together. So, but great question. Okay, so another question that comes up in this space is, you know, the sort of a more formal definition of provenance auditing and causal dependency tracking. So provenance, you know, is really you're logging the sequence of transformations in the space. You know, what had to happen to get you from here to there. Okay. Auditing is you have to log all the events, not only the successful transformations, but, you know, transformations that failed due to policy, transformations that failed due to quota, so on and so forth. So there's a bigger logging requirement and a bigger sequencing requirement for auditing than there is for provenance. And then causal dependency tracking is you're auditing and then you're logging reasons. All right, why did this policy fail? Which is even bigger. So the question, you know, from a community trust perspective is, how far do you have to go? Is provenance enough? Do we need full auditing? We don't know. You know, and it's going to be community specific, obviously, but you have to think through what these things mean for these communities, and the system has to be able to support what it is that you've decided in a fairly efficient way. And then, you know, what are the access controls on all of this? You know, do you have a different access control mechanism for the provenance and auditing than you do have for the security policies? Are they linked? We don't know. And then lastly, and this is the thing that everybody wants, but we haven't done, is what do we do about time series data? You know, in this carbon metric space, they would like real-time kinds of things. And there is, on the order of every 5 minutes, pricing data that's available. There's not a lot else that's available in real time so far, but you know, we're anticipating that. And then for sure, for SCiMMA, bringing it back to this community, you know, yeah, this is kind of what you want. You would like to be able to append data to a stream and have that then flow through the system. And this is our very, very latest thinking on this. There's this thing called the Lambda architecture. It's been around for a while, and it was originally you know, designed or hypothesized as a way to couple both batch processing and stream processing in a cloud. So if you've got, you know, click tracks or something, you're tracking your web traffic, you fork the data stream and pipe part of it through a stream query processing engine. And what that looks like is you define a query that the data matches, and you put that into the system. And every time you get a data match, a query success pops out. So instead of querying data that's static, the data's moving and your query is static. You sort of invert that. That's what stream processing looks like. And then you also pipe this data into what was HDFS, or which could be Spark, and then do analytics on it in batch mode. Okay, so what's a little bit different here is we're thinking that if we were to add a stream query layer, and Spark has Spark streams, so the technology nicely is there, could we then not only deliver stream queries to the front end, but use them as dependencies in the batch layer? Now that's new. That you don't see in this Lambda architecture stuff. So there's a new student who seems very excited about this, who I'm meeting with on Friday, who I'm going to try to convince to work with Kerem on this, because Kerem needs some help and some sleep. And so, but we think that this kind of thing, subject to everything else we've discussed, so, you know, the quota mechanisms, the dependency graphs, everything like that, would be able to handle time series data in the sense that you've got stream query processing, and you can set criteria for triggering materialization or triggering an announcement, not necessarily materialization, but triggering an announcement, so that these things are linked. And this would be, yeah, so this is our best thinking on what we might do that would be in some sense useful through that interface to a community like SCiMMA, and certainly to the carbon metric community. All right, so here's kind of the wrap up. You know, this complexity is coming really from two places. because it's complex, right? I mean, you've got this dashboard of data, and it's in all these different states, and you've got a notebook, and then there's graphs and blinky things and all this stuff. And so, which is good, but complex. And it really comes from two places. One is this lazy transformation idea. We're really using lazy transformation to do deduplication at a higher level. It's not bitwise deduplication, it's deduplication, based on consumption. And there's this kind of consumer pays model. Contributors don't get charged in this world for contributing. You get charged sort of for consuming. That's what we're really going for. So that accounting and this lazy transformation creates, kind of an interesting system. The other thing is that owner immutable access controls in this dependency space are weird. And this is the deal, right? I never understood why you could not take a public repo and make it private for like the first 5 years of GitHub. And the answer is because once it's public, there's no making it private. As soon as it's forked, you don't get the forks back. And so this has that property, right? If you try to make something less public, the materialization dependencies that your downstreams have defined may force a retention for something that you no longer want them to see. So it sort of looks like, if you want to do it this way, and you want to make a materialization guarantee, that you can't make things less public. You might go with this weak thing and just not allow a strong materialization by the consumer, and the consumer would have to know that that's something that isn't allowed. So there's this kind of communication now about whether I really want to consume your data set, which you need a mechanism for. And that's interesting. Access policies are probably not permissions in this space. This is weird, right? We've thought about permissions in a long time, but really what you have are restrictions. And the union of the restrictions is kind of what's governing whether you can materialize or not. No problem. Okay.
Adam had to drop, and I realized that we are actually at 3. So I wanted to hopefully ask if there are any questions from anybody. I'm happy to stay around for a couple more minutes if there are questions. Please use the raise hand feature or just unmute and go ahead.
Thank you for your patience.
And I do have a question, I suppose. I guess in the context of MMA and dealing with data that comes in and is part of manifestations, but might be incorrect. So for example, what happens if there's a retraction of a gravitational wave or an ice cube alert or something like this, and then that has become part of this? How does this entire depot system deal with potentially flawed data?
You would publish a new version. You would update your data set with either the data removed or it updated. The key thing is that you'd be able to see the flawed data. It doesn't go away. And so it will handle that, right? In the sense that that's kind of what you want. And if you deduplicated it bitwise, then it would actually be space efficient. It's just not prepared for you to have that flaw occur every 5 minutes, right? Or every 30 seconds where you're appending to this thing because new data has become available, something of that nature. No, that's a big deal in this space because, these data sets are constantly being cleaned. They're finding errors in them. We've looked at, electricity data, just at the consumer level, which is very, very private for some reason, and it's constantly got problems. So but what's key is that you don't see the problem. The problems don't disappear.
I have a question. I'm curious about discoverability. It seems like there's very little metadata or context about the data when it's uploaded, and so how is it indexed, or somebody's coming in and trying to find relevant data? How would one go about doing that?
Right. So we don't have a very sophisticated search mechanism at the moment. metadata is really organizational. What Kerem didn't talk about is that you're part of an organization, and the provenance is in some sense attached to that organization, and we have a way to attach metadata to that. What we don't have is a very sophisticated way to search that metadata, which you need. You need a way to say, I'm looking for a data set that looks sort of like this, and it was uploaded between this time frame and that time frame, and and maybe it came from this organization. It's EIA data or something of that nature. But you're absolutely right. I mean, the mechanisms for managing metadata are not there. What we have done, though, is attached those mechanisms to this notion of an organization, and that's kind of where the IAM lives as well in the system.
We have time for maybe one more question for Rich or Kerem.
It's me on Lively. I have a sort of a comment. So Rich is always predictable, thought-provoking. Now, being the cynic I am, I wonder whether the metaphor of a lake is a good one these days, given the picture that we have about what happened to lakes. But less cynical, and maybe along these lines, I didn't hear anything about what happens when things go wrong, when people deposit transformations that are not doing what they're supposed to do and crashing your system or filling up your disk. So in a policy, it was supposed to be less than, and it's greater than. You talked about auditing, you didn't talk about monitoring. And I don't know if all your safeguards are going to get into the accounting, but it sounds like a very utopic view of the world that everything works. Am I wrong?
Yes and no. So you're absolutely right. This is not a production system. A production system would have to have a very, very sophisticated monitoring capability. There's definitely a debugging capability. There is the notion.
But I thought that we as a community learned that doing something and then saying we'll turn it into a production system later cost us millions of dollars and a huge carbon footprint.
That was never the intention of this work. This was an exploratory. This is an exploration. It is what happens when you run these ideas logically to ground. To build this system requires a whole different engineering and thought process. The semantics are there. The semantics for update, for understanding the difference from one thing to another, that's all there. But this was just to see, what does this do, right, when you stand it up? It's an exploratory effort, not an effort to try and get you to use this software for some purpose other than to explore this space. Now, I think it's informed how I would think about trying to do this as a production system, no question. But no, we're not putting this software out so that Moreau and Livni can go build into OSG as production software.
Yeah, my only comment here is that if you have to put safeguards into policies, it has to go into the policies and it affects the logic of everything. So assuming that you can add all these things later while you are exploring all the interesting problems, I view that as a dangerous path, but that's me.
Okay. Well, I think you're right. I do think that these transformations have to be able to reason about exogenous circumstances. The network goes out, the disk crashes, blah, blah, blah. There's just no question that that's true. I think that the mechanism is there for doing that. Is it efficient? I don't know. Is it secure? I don't know. Right? There are these serious privacy and access control questions that you would have to work out, and maybe they can't be worked out. That's an entire possibility. But what's clear is that you can at least get this far.
So we are well over time at this point. I think.
Thank you very much, everybody, for your patience. I really appreciate it. And if you have any questions, by all means, get in touch. See you later.